So here we go. Once again, we want to thank you for joining us today. Typically, we give tours of the VLA because we, again, are all located in Socorro, New Mexico, just an hour east of the Very Large Array. But in addition to those tours, we have started doing themed tours to give a chance to highlight more that NRAO does and the other facilities that we have. So today's tour, today's theme is the Very Long Baseline Array, or VLBA. Most people don't know a lot about it, so we're really excited to tell you about it today. And one thing we just want you to keep in mind and bear with us is that Socorro internet is not the best or the fastest. So please forgive us for any technical difficulties. And again, you can let us know about those in the chat if you're having any technical difficulties that you think might be on our end. But otherwise, we want you to focus on using the Q&A feature for any questions. We will have dedicated time for questions at the end of the tour. We will also have 2 different guest speakers who will join us for that. So you can submit any questions you have during the tour or specifically for them once their segments start. And only use the chat if you need to let us know of some sort of problem. We will also share some of the links to the websites or web features that we talk about in the chat, but you will also receive a follow-up email from Zoom after the webinar with all of those links. So if you don't catch them in the chat, don't worry, you'll still get them. And just once again, links over here, questions over here. We love answering your questions, but there's a good chance that we might not be able to get to all of them. So if we didn't get a chance to answer yours, or if you think of another question anytime after today, we do have a very cool Ask an Astronomer feature on our webpage. The link will go in the chat and you will get it, but we have an astronomer on duty. And if you search the archives and you'd find that anything that you're looking to know is not already answered, you can ask a new question, and within 72 hours, someone will get back to you. Okay, so let's dive into the main topic for today, the Very Long Baseline Array. This instrument, we kind of refer to the entire thing as an observatory or a telescope or an instrument, but it's made up of 10 separate antennas that are scattered in various locations across North America, both in US states and territories. And all of the antennas are linked together and operated here in Socorro, New Mexico. The control room is located with us here. And the VLBA makes use of something that we call very long baseline interferometry. And I'll explain it a little bit more, but essentially it's interferometry, which is what we mean when we talk about combining signals from pairs of antennas over long baselines, meaning the distance between a pair of antennas. So the long baselines, meaning those antennas are very far apart. And for example, we'll get into the details of these particular antennas, but the distance between this one, our westernmost and our easternmost, is actually over half the diameter, almost half the diameter of the Earth. So that means it's going to be a very powerful instrument. So the good way to think about what very long baseline interferometry does for us is something my grad school advisor used to say: big is small, small is big. And what that means is the bigger the spread of the antennas on the ground, the smaller the detail that they can see on the sky. And the smaller the distance between the antennas on the ground, the larger the structure that they can see on the sky. And it's kind of equivalent to a zoom lens, which most people are familiar with if you use a camera. And even on your phone can do a zoom. So essentially that's what these telescopes allow us to do. We use this example when we're giving tours at the VLA because we have specific set configurations that the VLA can be in, but the largest one spreads the antennas out, so big spread on the ground to see small detail on the sky, and it essentially is 22 miles in diameter. And so then you can see that you get these tiny resolution of these smaller structures on the sky. And then if we take the VLA and put it in its smallest configuration, so small on the ground, big on the sky, you see that that same radio galaxy that we're looking at here now looks like this, because there's a lot of other emission that is on bigger diffuse scales, and in the in the largest configuration, you zoom in past all of that. So you miss what's happening. And so sometimes it's actually really useful to be able to do both of these types of observing. A great example of the big is small, small is big with the VLBA, which we're gonna go into more detail today, is this radio galaxy. Keep in mind, these are false colors. They're just showing brightness on the sky. But this big structure here is what the VLA saw when looking at this radio source. And this tiny little thing here, zoomed in, this is what the VLBA could see. So with its much longer baselines, much, much more small detail on the sky. So I mentioned earlier that the VLBA has 10 antennas located across North America. So there's one antenna at each station. That's a 25-meter dish, which is pretty much the same size as the VLA antennas, 25 meters in diameter, just over 80 feet in diameter. Each station also has a control building, and we always have roughly two technicians at each site who do the troubleshooting and the maintenance for each of the telescopes antennas. And during the observing runs, when all of these antennas are observing, at each of their stations, that's where the data is amplified, digitized, recorded. And then they actually have to send those recordings to New Mexico at DSOC. We'll let the operator that we have today tell you more about that, but it sounds like an old archaic process, but it's just faster way to get the data to us is to mail it through the mail than actually try and upload it, download it through the internet. One of the big differences between a VLA and a VLBA antenna is their base and how they rotate in what we call azimuth. So this is where they rotate to go from north to south to east to west. And the VLA antennas are actually permanently, they sit on 3 concrete piers. And so those piers don't move when the antennas are stationed there, but they have a bearing, a gear, essentially a ginormous circular gear halfway up the telescope that allows them to do this turning. The VLBA antennas, they actually sit on a single railroad track, which is just kind of crazy cool. So they actually have 4 railroad wheels that are stationed there, so the telescope turns on that track. Here's that's the part to sort of pay attention to. That's the difference between them. And I have a couple close-ups of what that looks like. So as you can see, it's a single railroad track, and that's one of 4 wheels that the telescope sits on. And then they both have a similar dish on top that moves in a similar way to point towards the horizon and towards the zenith. So I thought it would be fun just to sort of really show you in situ what each of these 10 antennas look like. So the farther and westernmost is Mauna Kea, which is a dormant volcano on the top of the Big Island of Hawaii. And you may have heard of it because it's an international site for astronomical observatories of all different types. There's optical telescopes up there, infrared, ultraviolet, and our radio one. And one of the good things about any kind of telescope location is our preference is always high and dry to get above the majority of Earth's atmosphere and above the moisture that's in that atmosphere. So Mauna Kea is, you know, a whopping 14,000 feet in altitude. So pretty high, makes pretty dry. The next one is Brewster, Washington. So I kind of included a map here for anyone who may be somewhat familiar with US geography, but not total. So it's kind of in the middle in the north of the state. It can get a lot of different types of weather. Owens Valley, California. So this one is here sort of in the Sierra, south of the Sierra and north of Death Valley, which is a very dry place. So that's good. It's actually near a town called Bishop, California, very tiny. The next one is Kitt Peak, Arizona. And like Mauna Kea, Kitt Peak is also a place where there are multiple observatories, some of which you can see in this picture here. And Kitt Peak is roughly just under 7,000 feet in altitude. And it's one of 22 telescopes that are on the site there. And now here in New Mexico, we're actually super lucky, and we get to have 2 out of the 10 VLBA antennas. The first one is in a place that is actually called Pie Town, for people that have never heard of it. There are 3 Pie Town restaurants there, and it's literally serves the greatest pie. And this antenna is just outside of Pie Town. And the second one in New Mexico is at Los Alamos National Laboratories. So that's kind of closer to Santa Fe. Pie Town itself, is just another 40 minutes west of the VLA. So from Socorro, we can get there quite fast. Again, Los Alamos. There's one in Texas, a little town called Fort Davis. And that's actually the highest town in Texas. So it's at 5,000 feet above sea level. And I'm guessing this photo is probably a very old photo from that coloring. And then we have one in Iowa, North Liberty, Iowa. So that's kind of near Iowa City, just west of Chicago. And this antenna actually hosts visitors. Students from the local universities and colleges can go there, and occasionally they will have public tours. Most of them, these antennas are in locations that you can't access, or if you can, it's still fenced off and we don't encourage visitors. But sometimes if you just check with your local one, there's a chance that they might, and all of the technicians usually are super happy to answer people's questions. All right, final one on the continental US is Hancock, New Hampshire. So super northeast and northwest of Boston. And this is the oldest town in America to host one of these antennas, which is pretty cool. And that one also will have the terrible winter weather and nice summer weather. You can hear more about that when we talk to the operator, Jessica, again. And lastly, the easternmost antenna is in the US Virgin Islands on St. Croix. And that is just to the east of Puerto Rico, and the Caribbean Windward Islands all start here. And this one is also unique. We normally have little heaters on top of the, what we call the feed horns, where the signals get sent into the receivers. And St. Croix, because it's so nice and tropical, doesn't need them, so we could take them away. But the con of being there is all of this salt water, meaning salty air. So it's a battle of corrosion that does happen there, and the dish has to be painted much more often. And occasionally has to deal with hurricanes, which it did in the last couple of years. Okay, so the VLBA can be even more powerful than just itself. So we talked about how the power of the VLBA is its long baselines, but it has the power to partner with other instruments and observatories around the world, creating even more long baselines, sort of upping the ante, as you will. It has observed with other instruments and telescopes in all 7 continents, including Antarctica, and a few orbiting spacecraft. So just to highlight a little of those, this is the Antarctic telescope. This is the German Antarctic Receiving Station. It was established here in 1991, and it's run by Germany's space agency, DLR, and it tracks satellites, but it also can cover satellites that are not seen by any other telescopes on Earth. So if they go around the South Pole, they would normally lose contact with their other tracking satellites. And these are 2 of the orbiting telescopes that the VLBA has observed simultaneously with. This one on the left is HELCA, the Highly Advanced Laboratory for Communications and Astronomy. That's built by Japan. And the one on the right is a Russian satellite, Radio Astron. And one of the really cool things is that as part of the early science program with Radio Astron, it joined not only the VLBA, but also the Green Bank Telescope and the VLA. And together, the resolution that that entire combined system had was 1/10,000th of an arc second. And if you don't know what that means, it's okay. It just is several hundred times better than the resolution of the Hubble Space Telescope, and the highest resolution ever achieved in astronomy. Another thing the VLBA is used for is it can be triggered by other astronomical phenomenon or observations, and then asked to slew over to point at those targets and see what's happening after whatever the initial event was. And some of those events are gamma ray bursts. So these are bursts of gamma ray radiation, which is the highest frequency of light that we are able to detect. And if you actually take the radio telescope and look afterwards, there is a little bit of a radio afterglow. So that's what this is showing. This is an actual observation of a gamma ray burst in the 90s. And then for those of you that have heard of LIGO and gravitational waves, black holes merging, but also specifically the gravitational waves detection that dealt with neutron stars, a pair of neutron stars merging, the VLBA was key in doing a follow-up observation to that. And that was even more interesting because the VLBA is observing radio wavelengths, which are a type of light in the electromagnetic spectrum, but gravitational waves are a completely different messenger, so to speak. So those are ripples in space-time. So this was a really cool way to show that these events not only produced gravitational waves, but they also produced electromagnetic radiation. And now perhaps one of maybe the least known, but to me, one of the coolest things with the VLBA is that it literally can be used to study everything from the ground that you're standing on to the farthest objects in space. And what I mean by the ground you're standing on is that it is actually a part of an international terrestrial reference frame. And so the 10 VLBA antennas are some of the most precisely known spots on the surface of the Earth. And this is important because it essentially, this reference frame is tracking how the surface of the Earth, where locations are with respect to each other, and then also how they're moving over time. So one of the things that the terrestrial reference frame really helped solidify was the acceptance of plate tectonics as a theory, prior to having a lot of evidence really showing that parts of the Earth were drifting and moving away and towards from each other. That was really hard for a lot of geologists to believe until they were faced with this kind of evidence. And the VLBA played a key role in just adding to that evidence. And it can also be used to track Earth rotations, and even locations of quasars in space can help solidify the locations of the telescopes on Earth. It works both ways. So what I would like to do now is actually ask one of our tour guides, who's a grad student at New Mexico Tech, Montana Williams, to join me. I'm going to stop sharing. And Montana, if you turn your camera on. I thought I stopped sharing. Yes, I did. So hi, Montana.
Hi, Summer.
I would love to hear more about your research, what your research area is, and how the VLBA actually plays a role in your research.
For sure. So I work with cute radio stars. And what those are is they're just stars that emit in their radio, and I happen to think that they're very cute. There's nothing too abnormal about them. So every star technically radiates in radio. We just usually don't see it because it's very faint emission. So we have like some radio data of our sun in the radio. So that's really cool. And more specifically, what I do with them is I'm just curious about their nature. So when I was an undergraduate, actually, I proposed to get time on the VLBA. Which was really daunting at first because when you write the proposal, you write both the scientific justification. So I was saying like, hi, I would like to look at these radio stars because I think they're really cute. Please give me cute images. And then I had to write the technical justification, which was very tricky because then I had to go in and like tell them what I wanted the correlator to be set up as and all of those things. And I had never actually done radio astronomy before that. So it was really weird to like suddenly be trying to say I want to do this with radio astronomy when I didn't know what it was. But through that process, I learned a lot about radio astronomy and more about radio stars. And so that's actually what geared me to do radio astronomy, is another really cool thing. And that's why I'm here.
Well, that's so cool. So the VLBA plays a role in your origin story.
Yes, it is the antenna or the array that is my origin story. But what do I do with my data? So I have observed data. I have proposed to get the data. I've calibrated some of the data. And so what I'm interested in is seeing what those radio stars look like in the radio, because that can tell us things about like stellar theory. It can tell us about like what the magnetic fields are doing with the stars, or just kind of understanding these cool stars.
And the VLBA is better for that than like the VLBA because
the stars are point sources. And so when we observe, we want to observe basically the star itself and like any like the atmosphere of the star. And so because the VLBA is so big and acts like a dish like the size of the United States, we can really see like all those like details in a sense and get a lot more information about the star versus just it's there, it's a radio star.
Right. Or here's a picture of 100 radio stars.
Yeah.
Like, no, I want to look at this one.
Yeah. And so there's actually some of them where they've been able to get like the stellar diameter from like the images. So we can actually see basically the full star, and like you kind of see like the dips and emissions. So you're getting like a picture of the star in radio. So it's really cool.
That is fantastic.
Cool.
Yeah. And so what stage of your PhD are you in right now?
I'm finishing up classes, and I've been doing a little bit of the research on it. So mostly I've been just calibrating the data and trying to figure out how to calibrate the radio data, which is really cool. And it's different for the VLBA than the VLA almost entirely. So that's another interesting thing.
It's no small task, I've heard.
It's not, especially when you're learning it for the first time, because you're giving it all these commands of, I want you to use this antenna as a reference antenna, and I want to tell you to like use this as a calibrator and all of these things. You're like, but what is a calibrator? And so it's really cool.
Yeah. Fantastic. Well, thank you so much for sharing.
Yeah, thank you.
Okay. So if you turn your camera off, and if I will share just briefly because I want to introduce who's coming up next. So our next guest speaker, which we're super excited to have with us, is one of the operators of the VLBA telescope. So Jessica King works here at NRAO, and she is an operations specialist. And this is a picture of her in the VLBA control room, which actually right now to me is just on the other side of my wall over here. And she's sitting in there right now, so she can show you around. And my colleague Faith is going to have a conversation with Jessica. So let me stop sharing. And Faith and Jessica, why don't you turn your cameras on? And I will go off and hand it over to you, Faith.
Hey everyone. So thanks so much for joining us, Jessica. We're really excited to have you and excited to hear about what you do.
Thank you. I'm excited to be here.
So why don't you start by telling us about yourself? So what's your background and how did you come to be here at the VLBA?
Okay, so I graduated from Vassar College back in 2014. I have a double major in astronomy and physics. And while I was at Vassar, I was working with the optical telescope there. They had this beautiful Schmidt-Cassegrain with a 32-inch primary mirror, and I just loved working with that telescope. I loved operating it. I loved troubleshooting it. I loved taking the data. So that's what I decided I wanted to do. I wanted to go into being a telescope operator. So after 3 years of rigorous searching, I saw an opportunity come up for the VLBA, and I thought to myself, that would be the coolest, like the epitome of being a telescope operator for me. So I applied, and here I am.
Yeah, that's true. It doesn't get much cooler than getting to control a telescope that's the size of a continent, right?
Exactly.
So, what's an average day at your job like? Like, what sort of things do you do regularly as an operator?
So we actually are in charge of a lot of different things. So we're in charge of pre-processing projects. So once projects get scheduled to run on our telescopes, we are in charge of sending the project scripts out to the telescope so that they know, okay, here's what we're looking at, here's the recording schedule. And we also have to post-process the projects as well, get the monitor data, check the pulse cal information, which is just a fancy measurement of the signal that's going through the antennas. And we also have to, of course, while the project is running, we have to keep an eye on the antennas and make sure that they're doing what they're supposed to, because they like to not. And so we have to make sure that they're that the timing is correct at each station, because each station have to have exactly precise timing in order for us to actually correlate the data afterwards. And of course, we have to make sure that there's no horrible faults happening. Like, we have a lot of issues with like the focus rotation module at the apex of the antennas. Those like to get stuck a lot, especially in the cold weather. And of course, we have to make sure that the elevation and the azimuth motors are functioning properly. And we also have to monitor the cryos, because all the receivers have to be kept very, very cold. Excuse me, very, very cold. So we have to monitor those and make sure that there's no issues, because those also like to malfunction. And we also have to correlate the data. So actually, what I can do is I can show you. So this is the monitoring station. We have these two giant screens up right here. So this is our main operating page. We can keep an eye on all the antennas right here. Right now, we actually have two different projects running. So we have some pointing files that are going on at most of the sites. And then one of them is actually running a track sun program. That's our Hancock antenna in New Hampshire. So this is where we monitor everything. We've got this scary looking alert screen right here that shows us generally like what kind of major problems are going on. We have a chat screen so we can talk to our site techs. We have, I know you can't see super well, but the cryo monitoring screen. We also keep an eye on the weather at all the sites. And then over here, we just have like couple of extra terminals that we use. I've got another weather screen up here, and we also have a web page open so that we can keep track of like what projects are coming up, as well as like general searches on stuff we need to do. And real quick, I'm just going to take you over here. So we are running correlation right now. So we're taking all the data from all 10 sites and combining it into one useful package that the scientists can then reduce down. And over here, so these are our playback units. So the packs come in from the sites. As we were talking about earlier, we have them on these big giant, like pretty much giant flash drives. So they get sent here to our operation center, and then we put them up on the wall, and then we can correlate from there.
And there's a lot of them.
Yes, we have a lot of packs, and we have a lot of units we can use. So they're actually correlating right now. So we have a lot to keep track of here.
Yeah, I was going to say there's a lot going on between all your different screens and everything that you have to keep track of at any given time.
Yes, it's very important to be diligent. because there's like a major problem, we have to try to be on it like that, or
Right.
risk, damaging these $1 million instruments.
Right. And from what I understand, the VLBA operators operate on shifts solo, right? And your shifts vary a lot, like between when you're working.
Correct. So we're on rotating shifts. So during the week we do 8-hour shifts, and then on weekends we have 12-hour shifts. So it goes basically we do 5 days of day shift, 5 days of evenings, and then 5 days of midnights. And then we have to go into doing the 12-hour midnight shifts. So for example, next week I'm going to be doing 5 days of 8-hour midnights.
Oh, wow. Yeah. Crazy for the sleep schedule, huh?
It is. It is. It can be brutal, but I love what I do, so it's really not that big of an issue for me.
Yeah, that seems like it would be very important in a job like that too. So
For
it
sure.
looks really cool. And how long, so when the VLBA is taking an observation, on average, how long do those observations last?
So they can range anywhere from 2 hours to 24 hours. On
Wow.
average, yeah, we do 24-hour projects. So on average, the projects are usually like 6 to 8 hours long. But we do we've also done really short ones that are less than an hour, but typically they're any range from 2 to 24 hours.
Yeah, makes sense. And of course, like Summer already told us, the antennas are in widely varying locations. So they are experiencing very different weather and environments at any given time. So do you have any particular antennas that pose greater challenges for you than others?
So I would say our Hancock antenna in New Hampshire definitely has a lot of New England weather. So a lot of snowstorms, a lot of nor'easters. So that one's tricky, especially in the winter. Our North Liberty antenna also has a lot of snowstorms to deal with. Sorry, that's the Iowa antenna. It also gets very, very cold there. Like it's actually our coldest site.
Interesting.
Yeah, so once the antennas get to below freezing, like below 0 degrees Fahrenheit, like we have to pull them for the safety of the antenna. And we actually had 1 week in January where North Liberty was out for the whole week because it was
Oh,
just constantly below 0 Fahrenheit.
oh dear.
Yeah. Brewster, of course, also Brewster, Washington also gets snowstorms. And with our St. Croix antenna, that one, the biggest issue we really have to worry about is, windy conditions and hurricanes.
Yeah, yeah, that's true. And so for new developments with the VLBA, have there been any recent exciting upgrades or new things added to the VLBA?
Yeah, so we've actually been working on upgrading our internet at all the sites. And because of that, all the sites actually have the internet capability now to do real-time fringing, which is really cool because in the past, what we've had to do was we've had to run, if we wanted to check that the antennas were fringing, we had to run these very short, very, very short 15-second fringe checks. So what that would do is it would take a 15-second recording of data, and then we had to download that to here in order to correlate that data. But now with the internet upgrade, we're actually able to see the data coming in real time, which is very exciting. So that's still in development, but it's something that they're going to be rolling out very soon that we'll actually be able to test on a regular basis. So that'll be really exciting if we can actually see the data coming in real time.
Yeah, that sounds awesome. And so many scientists use the VLBA from all over the world, right? So you can be in any country to use it. Is that correct?
Correct. We do a lot of projects for a lot of different countries, anywhere from Chile, Mexico, Italy, Germany, Russia, China, Japan. We do projects from all over.
And students get to use it too, right? Because Montana told us about her experience of using it as a college student. Do high schoolers get to use it? Do many college students get to use it as well? Or is it primarily scientists?
It is primarily scientists, but we do run student projects as well. Like I know that there have been a lot of like graduate students who have used our telescopes to do their thesis. Um, and I I know that they have like a summer student program. So in the summer, we actually run more student projects than we normally do, but we're definitely open to running student projects.
Awesome. And they just would have to submit a proposal for that, right?
Yes, they do have to go through the proposal submission process, but of course, with the help of their like advisors or the contacts that or the scientists that they're working with here at the NRAO, we work with them on that.
Yeah, makes sense. Oh, one that we got from the Q&A for you as well. So do you operate as the duty officer in coordinating repairs to the 10 telescopes that are so many miles apart?
Yes, we do. So our site techs at all the sites are on call 24/7. Um, they don't get a break, sadly. So so especially like during the day, it's the site techs are of course like on site, so they're also able to monitor their antennas. But once they're off shift and on call, it's up to us to keep an eye out for any problems that are happening, and we have to notify them and let them know as soon as possible, so that they can get out there and fix it. There are some things that are not like huge priority, like if there's a cryo that warms, but it's for a receiver that we're not using until like the next day, then stuff like that can wait until morning. But if it's like a serious motor problem, then we have to notify the
Right.
site techs and they have to get out there and get it fixed.
Yeah, makes sense. And then, so what kind of like collaborations does the VLBA do with other telescopes? You work with the VLA, and do you do many projects with other telescopes as well?
We do actually. So we also do projects with Green Bank, but we also do projects with the what's the VLBI. So we do a lot of projects that involve a lot of the European telescopes as part of the VLBI initiative. So a lot like in Germany, we work with a couple of telescopes in Sweden, Italy, Spain, and of course we also there's I believe you can pull up actually there's a map of the VLBI antennas. If you pull that up, you can see like there's so many, and we actually collaborate with quite a lot of those.
Great.
So yeah, we work with telescopes all over the world, which is really cool.
Sure. And then we also have a question about like, can you explain how the data from each antenna is combined together in a bit more detail, just like how it's added back together once it gets sent to Socorro?
So it's kind of a complicated process, but basically what it's doing is we're taking the radiation and we're translating it into a voltage. And that voltage actually retains the information, like the amplitude and the phase of the original signal. So we can take that and essentially add those voltages together so that it effectively makes like one super telescope's data. And then we can take that voltage and retranslate it back into what the signal would have been. So it's a very complicated process because we have to be extremely accurate with our station timing down to nanoseconds. So
Right.
that's why it's very, very important that all of our stations are in sync, because otherwise the data kind of gets a little messed up.
Right. Yeah.
So that's kind of like little more technical gist of it. But the data goes through a lot of different transformation processes.
Yeah. And since you're getting so much, it would no doubt be really important for it to be synced so exactly, just because otherwise it'd be really easy for it to get thrown off because there's so much of it.
Yes,
And then
exactly.
And then speaking of the data, so when observations are taking place, do you ever directly work with or coordinate with the scientists who made the proposal for those projects? Like, do you talk to them ever?
Unfortunately, we don't get to do that a whole lot. There's a couple of staff scientists that we do work with. Usually, when they're running tests, like sometimes they'll call us and like ask how how the test project is going. But we unfortunately don't really get to coordinate with most of the scientists during their projects. But of course, we do send an email out afterwards to let them know like your project ran and then any like potential problems that there might have been.
Yeah. Yeah, makes sense. All right. Well, thank you so much for telling us all about what you do, Jessica. This has been really fascinating, and we're still going to get to continue talking. We're just now going to open up to Q&A from our audience. Well, more. I asked you a couple questions from our Q&A, but we can continue that.
All right.
So here's one from the Q&A. Can the VLBA operate if one or more of the antennas are out of service?
Yes, they can. So it kind of depends on the nature of the project that we're running. Like some scientists request that there are a certain number of antennas are available. So it really depends on what the scientist is looking for. But generally, yes, we can operate with one telescope out, two telescopes out, sometimes three. It just really depends on what the scientist wants.
Yeah, makes sense. Let's see. So we have, how long does it take to correlate all of the baselines once the data arrives?
It depends on it depends on the size of the actual data. Like some projects record in much higher bit rates than others. So it kind of depends. Typically though, it takes about 70% of the time that the actual observation ran. So for example, if we have like a 1 hour project that ran, to correlate it takes about like 30 to 35 or 30 to 40 minutes rather.
Awesome. And we have another one here that says, hello, your job is amazing. What has been the most interesting discovery that you've witnessed at the VLBA?
Ooh, the most interesting. We do a lot of really interesting work. We observe so many different projects, like from like black hole research to star formation, galaxy formation, quasars, blazars. Like we do so much really fascinating work. I think recently, one of the coolest things was they successfully used our telescopes to bounce a signal off the surface of the moon, and they were able to map the surface just using that radio signal. So that's really exciting because that could pave the way for future exoplanet discoveries and further exoplanet research, maybe on their surfaces.
Yeah, that's great. Let's see. Wow, we have a lot of great questions in here. How powerful of a computer is needed to reduce the data?
Very.
Yeah, with that much data.
Yeah, so I'm not exactly sure like what kind of power specifically that we're looking at, but we have a lot of different correlator nodes that are behind the racks that I showed you. I think there's 20 or so of them. So we basically have like 20 supercomputers sitting back there combing through all this data and correlating it. Unfortunately, I don't have any more specifics than that.
Right. Yeah. No problem. So what's the most difficult troubleshooting you've had to do while the VLBA is observing?
Ooh, I would say I get really persnickety about the motors and the motor currents, because I'm always afraid that I'm always afraid that I'm putting too much stress on the motors, especially in winter when it's really icy. So I think because having a blown azimuth or elevation motor can be very hazardous. To my health as well as the antennas. So like recently, one of our antennas had an elevation motor that just completely failed. I mean, it wasn't anybody's fault. It just failed. And so what happened was the dish actually was not able to hold itself up. So it went like this, and it was horrifying.
Oh no. Oh gosh, that sounds awful.
Yeah, so I would say that that's definitely like the thing that makes me the most nervous is just putting too much strain on the motors.
Yeah, and I'd imagine too, like not being able to physically see what's going on there too probably makes it more difficult because you just sort of have to use your imagination to
Yeah, exactly, especially in winter when you're doing a night shift and it's dark, but you know it's icy, but you don't know how bad it is or if there's like
yeah.
just a new layer of frost forming. It's just that definitely worries me the most.
Yeah, yeah, makes sense. And so, was the location of the antennas planned in advance to be able to do interferometry properly, or did the calculations for the baselines come after after the antennas were built and installed?
So from my understanding, the general areas were planned out when they were planning the VLBA. So they picked out 10 like ideal locations just in a general area. Like they knew they wanted one in like the northeast and one a little bit more westward from there, et cetera, et cetera.
Yeah.
So they did the general planning and then they went in and pinpointed locations based on cost, how far away they were from big cities and a lot of big RFI sources. Um, so that was my understanding was that they had a general plan and then they went to specifics just based on little factors like that.
Cool. And how fast can the VLBA antennas get to their target? So from whatever they're pointing at now to if you point to a new target, how fast can they move to it?
So they actually move surprisingly fast. Let me see. I think I have a note here somewhere about how fast they actually slew. Yes, I do. So for azimuth, they slew about 90 degrees per minute. For elevation, it's 30 degrees per minute.
Interesting. Nice. So so just to remind everybody at home too, so since azimuth is the north south like direction wise, that means it can go I guess an entirely different direction, so from dead north to dead east or so on in a minute. Wow.
Mhm.
Wow. That's
Yeah,
awesome.
they're huge instruments and they move surprisingly fast.
Yeah, and then altitude 30 degrees. Yeah, that is really really fast.
Hmm. And
All
it's
right.
incredible to see.
Yeah. Yeah. And then, so what is your usual signal to noise ratio? Because of course there's noise caused by a lot of other radio sources, of which there are a lot. And so how do you extract the real signal that you're trying to look at from space from the noise?
Um, so that can be a tricky process. It kind of depends on the strength of your source. But basically, so that's something that gets more involved in the actual processing of the data that the scientist does afterwards. So it's kind of up to them to sort through and they have to be aware of what the weather conditions were. They have to be aware of like any potential problems that the antennas were having. And I can kind of speak a little bit on this because I have run my own project on the VLBA and I did actually post process that. So all of my sources were fairly strong though, so it's kind of up to you to sort out like okay, you can kind of see generally like if you have like a like in your data, you'll see like a spike in amplitude or even just like a little bump in amplitude, but you're like, okay, this is going to be my source. This is what I was looking at. And so you can actually filter all the rest of it out using apes or casa or whatever program you're using. So that's definitely a lot more of the data processing step. Like we here on the operator end, basically what we do to reduce the noise is we have to make sure that the receivers are as cold as possible. And we will note in the logs if we see anything strange, like if RMS counts are really high, which is basically like an indicator of noise. But that's about all we do from our end. It's mostly up to the scientist reducing the data.
Great. Yeah. And then here's one about another personal question for you. So did you have any difficulties working and studying in STEM as like, and then do you have any suggestions to young girls who want to get a job like yours?
Oh, that's a great question. So I think that being a woman trying to get into STEM is obviously not an easy task just because it's such a male dominated field. At Vassar, I was pretty fortunate because Vassar is still predominantly female. But in my classes, I was taking like high level astronomy, high level physics. They were still male dominated classes. And sometimes I felt like it was difficult for me to be taken seriously as a woman. But what my advice to any young girls who are watching, who want to get into science, like, be a force to be reckoned with. Like, like, don't ever let anybody tell you what you can or can't do. Like you can do it. You are capable. You are just as competent as men. Don't let men like try to walk all over you. Be be strong. Like, you can do it.
Absolutely.
It is a tough field to break into, but if you just keep at it and you just don't give up, then you will get there. It took me 3 years after I graduated to find this job, but I didn't give up. I kept at it, and here I am now. So just don't give up, believe in yourself, be strong, and show those men that you can do it.
For sure. Yeah. Here you are having the time of your life, right? And nobody can tell you what you can or can't do except yourself. So
Exactly.
yeah. All right. So I think that is a great question to end on. So thank you so much again, Jessica, for being here today and taking the time to talk to us and tell us about all this great stuff. This was such great information, and I hope everyone else really enjoyed it too.
I hope so too. And thank you so much for having me. And thank you for everybody who's here watching.
Of course. And okay, so now we're just going to wrap up here. So just have a few more slides for you. So for anyone who wants to see learn more about the VLBA, all 10 antennas have their own webcams. And so you can look and see what the webcams are currently seeing at any of the 10 sites. And we'll have the link to those. Thank you, Montana. Montana just put those in the chat. And again, they'll also be in the email that you'll get at the end of this session. So they update every 10 minutes from what I understand, except the Los Alamos one that isn't in real time, but the other ones update every 10 minutes. Is that correct?
Yes, correct.
Awesome. And yes, and so next month, we're going to have another virtual tour on March 27th, same time, 1 p.m. That'll be Mountain Daylight Time. We'll be on daylight savings by then. So you can register for that as well on our website. And we hope you'll come to that as well. So that'll be talking about what we want the future of the Very Large Array to look like. And yes, thank you everyone so much for coming. We really appreciate you being here, and have a great rest of your weekend.